everybody, and welcome back to another installment of Functions as Cornerstones of Algebra 2 with me, Mr. Poley. I'm your guide for this morning. Okay, we are moving on today and learning about inverse functions. Okay, our most recent lesson before today was one-to-one functions, and now we are moving on to inverse functions. So I know that's a word you have heard before. Whether or not you know what it means right now, that's another story, but I know you're at least familiar with that word. Okay, we are on page 61 and 62 today. That is what is behind me. I'm hoping we have some better luck with the lighting on the screen. It looks like it's being a little bit better than the other day, so we're going to do the best as always. Okay, it is another gloomy morning, but I was trying to avoid that just because it's been gloomy all week. So I don't know what's going on, but I'm not going to bring that up anymore because I feel like that's just keeping that gray shadow over Hannibal right now. We got to clear things out and let the sun shine through. Okay? So inverse functions. Here we go. If you guys notice, behind me here, I'm at the top of page 61. Okay, this is where our inverse function notes begin. And maybe you guys notice, if you even looked at it yet, in C and D, what do we have here in C and D? Before I even explain anything. Okay, hopefully you guys recognize those as compositions of functions. Okay, we actually ended the last question on the function composition homework was about inverse functions. That was why I had you guys do that one, and I had you guys try to explain what was happening within those functions. Okay, or within that composition. And really what's happening is those two functions were undoing each other. That's the whole idea of this inverse function, or inverse functions, is that one function undoes what the other one already did. Okay, and the idea of these inverses, or you could almost think them as being opposites of each other, they're very important in mathematics. You guys have used inverses your whole entire mathematical careers. Right? Adding and subtracting. Those are two inverse operations. Can you think of two others or another pair of inverse operations? I'll give you a second to think. Then we divide. Right? Multiplication and division. Those are also two inverse operations. They undo one another. Okay, and those are things, like I said, you've been working with for years and years and years. Right? Another example of inverse operations. I know I mentioned it before. Can anybody think about the other one I'm thinking of? It involves maybe an exponent and then some other fancy symbol type thing. Squaring and square rooting. Okay? If you square something and then you square root that result, those are inverse operations. Okay? Square rooting undoes what the squaring did, or vice versa. Okay? They are opposites of each other. They undo what the other one did. So we're going to work with that idea, just the general idea of inverse functions today. Okay, but first we're going to consider these two linear functions given by the formulas. We have f of x equals 3x plus 7 over 2. Then we have g of x equals 2x minus 7 over 3. Okay? If you guys notice, I hope that you notice. I hope that you notice things all the time, right? Be aware. Be aware of what's going on. Observe things that are around you in the context, right? So if you notice here, you've really got similar functions, similar formulas here. Both have a 3 somewhere, both have a 2, and both have a 7. Although 1 7 is being added, 1 is being taken away. 1 7 is being added, 1's being taken away. Sounds like some inverse operation going on. Okay, so we're going to calculate a few of these things here and see what's actually happening. So my first one says to calculate f of 5. Okay, so that means I take my f of x function, substitute in 5, 3 times 5, 7 over 2. So that comes out to be 11. So f of 5 is 11. And now they're asking us to evaluate g of 11. So it's basically like they're giving us, we have a composition here, just not, it doesn't look like a composition, right? They didn't put one inside the other. They're just asking us to do them two separately. So let's see what we do, what we get when we do g of 11. So I'm substituting in 11. Okay, I have 2 times 11 minus 7 over 3. That comes out to be 5. So looky there. What we were told to evaluate for f was our final output when we evaluated that for g. See how that works there? Okay, what happens when we do f of 0? Any guesses here based on what else they told us to evaluate? Okay, when we evaluate this for 0, that does come out to be 7 over 2. What about when we do g of 7 over 2? This one's a little trickier just with the fraction that we need to evaluate for, so I will write this one out. We have 2 parentheses 7 over 2 minus 7 all over 3. Okay, and in the numerator, we focus on the numerator first. We have that 2 times 7 over 2. Well, those 2's will cancel because we're multiplying and dividing by 2. So those are gone. That leaves us with 7 minus 7, which is 0 over 3, which is simply 0. You can have a 0 on top of a fraction, right? You can try to divide into 0, but you can't divide by 0. Okay, so that does come out to be 0. And again, we have f of 0 equals 7 halves. G of 7 halves equals 0. A little back and forth action going on. Okay, calculate f of g of negative 1. Oops. Any guesses as to what that will be? I'm not going to take the time to evaluate those. You guys should do those on your own. Okay, you do g of negative 1. Now, whatever you get for that output, evaluate that then for f. So this does come out to be negative 1. Original input is your final output. Final output is your original input. Calculating f of g of 5. What do you guys think here? Well, you should go through and do that. Okay? Compute that one. Calculate it. Make sure that your final output is equal to 5. I'm going to put that there with a question mark because that's for you guys to confirm, to verify. Okay? And our last one here, without calculation, determine the value of f of g of pi. F of g of pi. Good thing they're telling us not to calculate it because that could get a little messy with pi in there being as irrational as it is. You know, like get rational pi. Okay, what does that come out to be? Again, I'll let you guys fill that in there. But think about everything that's happening here, okay? These are inverse functions, so they undo one another. Okay? Fun fact for you guys, f of g of pi, I have that pi symbol right here on my shoulder blade. It's because math is beautiful, and I never want to forget it. All right, moving on down here. The two functions seen in exercise 1 are inverses because they literally undo one another. Right? They undo one another. Looking at those formulas again, 3 times x plus 7 over 2. Well, then what's happening over here? 2 times x minus 7 over 3. So here we were multiplying by 3. Here we're ultimately dividing by 3. Here we add 7. Here we subtract 7. Here we divide by 2. Here we multiply by 2. So you can see everything in each of those formulas is literally the opposite of the other formula. Okay, that is how they undo each other. They're doing the opposites. So the general idea of inverses, f of x and g of x, is shown in this mapping diagram here. Okay? So start over here. Start on the left where it says the domain of f. Okay, that's all our possible inputs that could go into this f of x function. And here they're naming all our inputs a. Okay, so if you have f of x, when the inputs go in, all those a inputs go in, the outputs are b. Okay, and then this shows that all the inputs go into the function and they come out as b. Those are your outputs. So all your outputs here, all these b values are your range. So a's as your inputs go in and come out as b's. Inputs, outputs. But now we kind of switch gears and turn back. Okay, now b's, which were the range, the outputs of f, those are now our domain of g. So if we take our b's and input those into g of x, as you see here, g of b gives us a as our output. And which we already discussed, a was originally our input of f. Okay, so your inputs go in to get your outputs. Those go into the inverse function to give you back your original inputs. Okay, and that honestly could just keep going around and around and around. Inverse functions, they are undoing one another. Start with a's, get your b's, back to a's. Okay? One thing about this notation here, this is function notation, and anytime you see something like this, that represents a specific point, right? Ordered pairs. So this f of a equals b, here a is our input, so that's our x, that's our x variable, or our x coordinate, and then b is our output, so that is our y. Okay? So any point ab is in our function f of x. Okay, this is just a general point that could represent any point that's in f of x. Then you'll see down here, now we have g of b equals a. I'm just going to draw another arrow over to here. Same idea. This represents a point, or many points really. Take our input, pair it with our output. Okay, so b comma a represents any possible point in our g of x function. Now, what do you notice between the two ordered pairs that I wrote down? Okay, for f of x, we have all the points a, b. The inverse function has all the points b, a. So we need to notice here, we need to recognize that with inverse functions, the coordinates switch. The x switches with your y. The inputs become the outputs, and the outputs become the inputs. Okay, AB on your inverse function becomes BA. Okay, they undo each other. The coordinates flip. The x and y switch places. Okay, that is true for every inverse function, and that is a huge idea to remember. Okay, your x's become your y's become your x's. So for exercise 2 here, use that idea. If the point negative 3, 5 lies on the graph of y equals f of x, then which of the following points must lie on the graph of its inverse? Okay, if negative 3, 5 is on f of x, then what point is on its inverse? Well, like we just looked at above, AB becomes BA. So negative 3, 5, little switcheroo to get the point on the inverse would be 5, negative 3. That should be choice 3. Okay, listen up right here. Everybody listening? Okay, a big common mistake, which I understand why it happens, but a common mistake is to take these points, or this point, these coordinates, and simply negate them. A lot of people hear inverse and they just want to throw negatives in there or negate what they already have. So the common mistake answer would be choice 1, 3, negative 5. But an inverse does not negate the coordinates. It does not negate the values. It does not negate the function. It just does the opposite of it. Okay, so negative 3, 5 becomes 5, negative 3. Okay, and we will discuss that more. Don't you worry. Alrighty now, get into the fun stuff. Wait a second, I thought we were having fun already. Oh, we were. Don't worry. Okay, here we go, on to the back. Inverse functions have their own special notation. Of course they do, because why wouldn't they? Okay, if a function y equals f of x has an inverse that is also a function, we represent it as y equals f to the negative 1x. Okay, and that is a reason that students and other people, teachers sometimes too, I'm sure, that's why they want to negate the function to get the inverse, because of this negative 1. Okay, that is not what that means though. That just means it's the inverse. Okay, don't fall for that. Do not throw negatives on there to get your inverse function. Okay, it's not what you do. Don't negate. You switch, reverse it, opposites, not negated. Okay? The linear function f of x equals 2/3 x minus 2 is shown graphed below. Oh, so this is nice. Now they're giving us an equation and the graph. We're going to use this graph to answer the following questions. Okay? Evaluate f inverse of 2. F inverse of 2. Think about what that means first. F inverse of 2 means that on our inverse function, x is 2. But we don't have our inverse function here. We have our original function. So if x is 2 for our inverse function, which that's what this shows, f inverse of 2, that means we're looking for in our original function, which is this, we need to find when f of x equals 2. Okay, because remember, this is the same as y equals 2. So if we know that x is 2 on our inverse function, we need to find where y is 2 on our original function. And you guys see that over my shoulder here? Y is 2. Y is equal to 2 at this point. The function f of x is equal to 2 at this point. Okay, and the function is equal to 2 there when x is equal to 6. F of x equals 2 here when x is equal to 6. So at this point here, that's the point 6, 2, right? And this is our original function. So that means our inverse, I'm going to label this arrow inverse. Our inverse function then must have the point 2, 6. Okay, can you see that over here? Our inverse must have the point 2, 6 if our original function has the point 6, 2. And that's exactly what this shows here. F inverse of 2 equals 6. That says on our inverse function, when x is 2, y is 6. It's exactly what we have here. Okay, so f inverse of 2 equals 6. What about f inverse of negative 4? Same idea. That's telling us that on the inverse function, f negative 1, our inverse function, x is negative 4. So that means we need to look at our original function here and find when f of x equals negative 4. And again, we're looking for when y equals negative 4. So look at that graph. Where is y equal to negative 4? Well, we go down 4, and that's the point right here. Okay, that is where y is equal to negative 4. And what point is that? That looks like it's the point negative 3, negative 4. And again, this is the point on our original function. So to find that point on our inverse, we simply switch those to get negative 4, negative 3. So again, this is a point on our inverse function. When x is negative 4, y is negative 3. That's what this is asking for. Find the value of the function the y value when x is -4. And we just showed that to be -3. Okay, so I'm using the fact that the coordinates switch places. Again, your x's become your y's, and your y's become your x's. You need to use that idea here to evaluate for the inverse function, because we don't have the inverse function on our graph right now. Okay, but you can still use that idea. All right, I'm going to clear this for a second. We now need to determine the y-intercept of f inverse of x. Okay, this is one of my favorite ideas here, my favorite concepts, my favorite question. I shouldn't say my favorite question, okay? That's a bit of a stretch, but it's one of my favorite questions to ask. What is true for every y-intercept? What is true for every y-intercept? Okay, can you guys show me on this graph here where our y-intercepts would be? Okay, everybody should be saying on the y-axis, this is where you'll find your y-intercept. This right here is the y-intercept of our original function. And what's true at this point? Okay, that's right, for every y-intercept, the x value is 0. The x value is 0 here. So the y-intercept of f inverse of x is the point 0. I'm just going to make that k because we don't know what that is. That's some unknown number right now. The y-intercept of f inverse of x will have this form. So that means if we only have our original function here to work with to get the y-intercept of our inverse, if we know this has to be the coordinates of our inverse y-intercept, we do a little switcheroo here, 0k becomes k0. So we need to find this point on our original function, because that value of k then will correspond to the y-intercept of our inverse function. All right? And you'll see how this all comes together in a minute here. So k of 0, we're looking for where y equals 0. And y equals 0 anywhere across this x-axis. Anywhere across this x-axis is where y equals 0. So the point we need is right here. That's the point we need. That's the silver tuna. Okay? And what is that point? That's the point 3, 0. So if this is on our original function, 3, 0, the inverse then, f -1, would be 0, 3. And 0, 3 is up here, which we can confirm that would be a y-intercept because it's right on the y-axis. So the y-intercept of f inverse of x is 0, 3. Okay? You guys believe me when I say I know this is a tricky concept. Okay? Inverse functions are confusing, I understand. But it's really about flipping the x's and y's and using that idea to your advantage here. Okay, I know that question is not easy. It's hard to wrap your head around. That's okay. Take some time here, rewatch what I said, that part of the video, really try to understand it and let that sink in. Okay, very important concept here that will continue through the course as we study other functions. Okay, so last part for this one says on the same set of axes, draw a graph of y equals f inverse of x. So we simply need to draw the inverse of this graph, of this function that's already here. Okay, and to do that, what do you guys think we should do? What have I been saying quite a bit since we started this lesson? Okay, the inverse function, it's the opposite function. The x's and the y's switch. So we're going to switch them like this. Switch the x, switch the y, just like this. Okay, let's see. Starting with this point over here, which we said was 6, 2. So that becomes 2, 6. And if it helps to write out these coordinates, please do that. Okay, we have 6, 2 right here. Here we have 3, 0. Here we have 0, negative 2. Here we have negative 3, negative 4. And here we have negative 6, negative 6. Okay? So hopefully you guys can see those there. Those are all our function, our original function points. Remember, for our inverse, f negative 1, those all switch. So that becomes 2, 6. This becomes 0, 3, like we established before for the y-intercept. This becomes negative 2, 0. This becomes negative 4, negative 3. And this one, since the coordinates are already the same, that one stays the same. See those over there? Okay, so negative 2, 0, negative 4, negative 3, and negative 6, negative 6. Use a straight edge here, connect these through. Boom. Label that f negative 1, f inverse of x. Okay, a function and its inverse are really quite beautiful when you put them together. Right, there's a little bit of some kind of a reflection going on. Hopefully you guys can see that, right? They're not just arranged in any old way. There's a pattern. There always is a pattern. Okay, guys, be aware. Notice your patterns here. If there was an invisible line maybe through the center here, that would... Visible line through the center, that's the line y equals x, the perfect diagonal line through there. These graphs are flipped, reflected over that line. Do you remember reflections from geometry? Okay, that's what's happening here. An inverse and its function are reflections, a reflection of each other over that line y equals x. Okay, but more about that later. Alrighty, last one here. You guys still with me? Check, check, 1, 2. All right, here we go. Table of values for the simple quadratic function, f of x equals x squared. X squared means this is quadratic. This is given below along with the graph, this nice, pretty parabola. Okay, so this is our original function, f of x, and here we have our table of values. Oops, zoom in a little bit. Okay. Well. Okay, from negative 2 to 2 are our x values, and then f of x, 4, 1, 0, 1, 4. So those points, those 5 points are right there. Okay, so graph the inverse by switching the ordered pairs, just like I showed you over here. Right, again, x's become y's, y's become x's. So negative 2, 4 becomes 4, negative 2. Negative 1, 1 becomes 1, negative 1. Okay, it should be filled in just like that. And now we should graph it. Okay, so 4, negative 2. Right there. 1, negative 1, right there. 0, 0. Boom. 1, 1. Boom again. 4, 2. Okay. So we've got 5 points here. We have 5 points. We want to connect that. We want to connect that with a nice curve, nice sideways parabola. Okay. So here we have f of x that should be labeled. And now what we just drew in is f inverse of x. Okay. The next question, the last question here, what do you notice about the graph of this function's inverse? The graph of this function's inverse. What do you guys notice? Well, hopefully based on what we said above, you can see that if we had an invisible, well, if we sketch that line y equals x here, you guys see that? You can a little more clearly see that this original parabola reflected, it's hard to, you get the idea though, right? It's reflected over that line, that dotted line y equals x to get our inverse function. Think of that line there as a mirror. Okay, these are mirror images of each other over that line. Okay, is there anything else you notice? I'm going to write in there, reflected over y equals x. Okay, again, that's that diagonal line through there. Anything else we notice? Well, let's see. It does not look like our inverse is actually a function, right? Would what we just drew in here, this sideways parabola, does that pass the vertical line test? No, it doesn't. So what do you notice about the graph of this function's inverse? The inverse is not a function. Okay, the inverse is not a function. That's important here. Okay, so even though our original quadratic, that is a function, our inverse is not. Okay, question following up from last lesson, is our original function 1 to 1? Is our original function 1 to 1? Does each input have a unique output? Well, let's see here. When we are at -1 as our input, our output is 1. When we're at 1 as our input, our output is also 1. So our original function is not 1 to 1. And another way you could have tested that was with that horizontal line test. Okay, draw your horizontal lines across, and you'll notice that you would hit in more than one place, which means the original function is not 1 to 1. And because the original function is not 1 to 1, because it fails that horizontal line test, that's why our inverse is not a function. Because our original was not 1 to 1, the inverse will not be a function. Okay, because right now it fails the horizontal line test. When you flip it, turn it sideways, reflect it over that line, it would then fail the vertical line test. So if the original fails the horizontal line test, the inverse will fail the vertical line test. So this box at the bottom here just sums that up for us. It says a function will have an inverse that is also a function if and only if it is 1 to 1. Hence, a quick way to know if a function has an inverse that is also a function is to apply the horizontal line test. Okay, right off the bat, I could have drawn horizontal lines through my original function here, and I would have seen that it failed the horizontal line test. That would tell me right away that the inverse is not a function. Okay? So some really big ideas in this lesson. Okay, some crazy kind of concepts. So I hope you take the time to let this sink in. Really try to understand what this lesson is offering us, what I'm offering you guys. Okay, rewatch some parts if you need to, and come prepared to class with questions for me. Okay, I know there will be questions. It's just a fact. There has to be. So please be ready to ask them. Okay, I want to help you guys understand this better. I appreciate you taking the time to watch this. Okay, so that is all for me now. By the way, it's hat day. And tomorrow I'm not going to be here, so that's why I'm also wearing my flannel. Okay, 2 spirit days in 1. Hope everybody else has their hat day on, and continue to have a nice day.